All right, in this example, we guess on each question of a 4-choice, multiple choice type quiz that has 6 questions. What is the probability you get at least a 50%? And this we're actually told to round to the 10,000th place. All right, so this is we're guessing. So guessing on each question, and there's 4 individual choices on each question. So the probability we get each question right is 1 out of 4. There's a total of 6 questions, so we're repeating this trial 6 times. So I'm going to count a success, getting the question correct. That's the thing that makes the most sense to count here, in my opinion. So n, there are 6 trials because there's 6 different questions. P, the probability of a success on each individual question is 1 out of 4 because there's 4 choices. And x, we're saying we want x to be, well, actually, we don't want x equals. We want the probability we get at least a 50% on the test. So 0, 1, 2, 3, 4, 5, or 6. This is the number of questions we could get correct. We want to get at least a 50%, so we want a 3 or greater. We want x to be greater than or equal to 3, because getting exactly 3 questions correct would be a 50%. All right, so this is starting to get a little bit more cumbersome. If I wanted to take these values and add them up, I could do that manual. I could use BinomialPDF 3 separate times. I could cite BinomialPDF with the 0 successes, 1 success, and 2 successes, add those up, and then use my complement rule. I think the easier thing here to do would be to introduce what's called the BinomialCDF. The BinomialCDF says, well, it's still going to be n, p, and x. So it's still going to be 10, 1/4, and then some number of successes. But this right here, this 2, is saying this is the probability of getting at most 2 successes. So if we use the BinomialCDF, what it's going to do is it's actually going to figure out the probability of getting 0 successes, the probability of 1 success, the probability of 2 successes, and add those 3 numbers together, all together to give us this BinomialCDF. The C stands for cumulative in this instance. The P, when we're talking about the BinomialPDF, that would stand for the binomial probability distribution function. This is the binomial cumulative distribution function. BinomialPDF, if I said, so the BinomialPDF was 6, 1/4, 2, this would be the probability of exactly 2 successes. So the BinomialCDF is good for when you want to cover a range of numbers, a range of different number of successes. Instead of just a single one, like this one, I would have to figure out the binomial PDF of 0, 1, 2, and add those 3 things together. That would ultimately give me the same as if I did this just the BinomialCDF with just a 2 in here. So 6, 1/4, 2. So let me go ahead and do this. BinomialCDF is in the same place as the BinomialPDF. I've scrolled past it a number of times. BinomialCDF, cumulative distribution function. We have an n of 6, a probability of 1/4, 0.25, and we're saying the probability of getting at most 2. I just realized I need to do 1 minus in front of this. Don't forget when you're dealing with these calculators, you can normally, if I was to just press 1 right now, it would overwrite this BinomialCDF. Instead, I want to change it to insert mode. You can see insert is right there above the delete key. So if I press second and then that key, it changes my cursor. This cursor is more like what you'd see if you were working in a word processor. It's the underline, the underscore that's flashing. So now if I type in a 1, it just pushes things over, and 1 minus. Like I said, this is much more what people are used to when they're working in word processors. Actually, the insert key on a keyboard does much the same thing. It changes between insert mode and overwrite mode. These calculators just default to overwrite mode all the time. I'm not sure exactly why they made that decision, but that's how they start. But most word processors default to insert mode. All right, in any case, 1 minus BinomialCDF. Okay, so I think that's everything we need there. And this gives us 0.169. We're rounding to the 10,000ths place. That would be hundreds, or tens, hundreds, thousand. I think I said tens. Tenths, hundredths, thousandths, 10,000ths. So we want to round to 4 decimal places. This is 0.1694. 1 minus BinomialCDF. 6 1/4 2 is approximately 0.1694. You'll notice that I did my complement rule as well, because this right here, the BinomialCDF, told us the probability of getting this stuff over here. I had to use the complement rule separately to figure out the probability of getting that stuff over there, the 3 or greater, and that's what we're actually after on this problem.